It's a pity that I cannot use much the blackboard, because our field is also theoretical, but it's more an applied field. So our main work is to solve equations with the computer and not on the blackboard. That's the reason, actually, at least in this course, we will not look at many equations, solve equations. We will look mainly at maps, and we'll discuss what we can learn from looking at global maps of climate parameters in the ocean and in the atmosphere. So, most of the course will actually be based on the following online textbook, which is not being written by me. Anyway, if you cannot read this, anyway, you can Google online textbook Oceanography. You will probably find it also. Okay. Let's see. So I'm the one who's starting the Earth system physics part in your course. And I should start with oceanography, actually, right? The problem is that I am a meteorologist. So as a meteorologist, have to talk a little bit about oceanography. And therefore, we will do that a little bit. But mainly, I will talk about the connecting part between the ocean and the atmosphere, which is the sea surface, essentially. So most of my talking about ocean will not be going into the deep ocean circulations, but we will talk about the surface connection between the ocean and the atmosphere. That's because I am more used to know about these things. There will be Riccardo Farnetti, who is also a researcher in our section, who will be talking about the real ocean stuff. So I will be giving 4 lectures, and Riccardo will give 2 lectures on the real ocean part. So that's something you have to keep in mind. So at least 3 of my lectures will be based on this web page, which hopefully is already here. Okay. Okay, we see. So this is the, no, you don't see. See if we see something. Okay, it will be probably becoming a little bit brighter, hopefully. So it's this textbook that I will be discussing, let's say 70% of this course. In the end, I will give a little bit of a different kind of perspective also, but essentially 70% based on this very nice textbook, which is really not so much, you can talk about many facts in the ocean, like what is the size of ocean basins, what are properties of water and things like this. But this book is really more based on mechanisms that are important to drive ocean circulations and so on. So if we go to the table of contents, yeah, then it's my pleasure to start to talk about the Earth system physics part, really. So I'm the first one who can talk about this whole subject of Earth system physics. And kind of we start to discuss this by looking at this diagram here. And this is exactly kind of summarizing what kind of research we are doing in our section, really. The people who do more chemistry-related stuff, climate-related things, related things to the ocean circulation, and related things also to the solid Earth. Almost everything is included in this diagram. And we are doing, if you want to, we are doing modeling of this Earth system as a whole, if you want to. And as you can see, it's already from this diagram is very, very complicated. So the traditional kernel of the Earth system physics study is probably, that's said from an atmospheric scientist point of view, probably the ocean-atmosphere coupled dynamics, which is really the basics that has been started in the 1950s already, or even earlier. So people have started to think about how to model these kind of things. Do you know what kind of equations are the base for modeling the atmospheric dynamics and the ocean dynamics? Yes, please. For example, the first law of thermodynamics is a very important equation we have to solve. And we have to solve, it's a partial differential equation because we want to solve this equation on each point of our globe. Also in the vertical, from the ground, or from the deep ocean, or from the deep Earth internal, up to wherever we are interested into the ionosphere. So it's a partial differential equation if we pose this equation at each point where we are interested in. For example, the thermodynamic equation. That's one. There are other equations.
I don't know, but I'm not sure, but the hydrodynamics?
Yes, hydrodynamics would be Navier-Stokes equations. You would call thermodynamic and the Navier-Stokes equations together thermohydrodynamic equation. So that's essentially the equation for conservation of momentum for the Navier-Stokes equation, and the equation for the conservation of energy for the thermodynamic equation. Essentially, we could name one more equation that is the real basic, is the conservation of mass. So it's the continuity equation. And this is kind of the absolute base. So any Earth system model that really, in a more serious sense, can be called Earth system model is based at least on these thermohydrodynamic equation, if you want. So if you want to write them down, they look like d by dt, and then we have the velocity, and then on the right-hand side we have terms that cause changes of the velocity. And we have something like d by dt of the temperature, and on the right-hand side we have terms that are changing locally the temperature. Have you come across this operator here? Good. Do you know what this is? This is the time derivative. For partial differential equations, there are two types of time derivative. This is the total derivative. Okay. So that means we are essentially following a partial and look what kind of causes changes if we imagine to follow this particle. And then there would be the momentum, the mass conservation equation is an equation for the density, and also there are terms that can change this. So these equations are coupled, and they have to be solved all over the globe. You can imagine how many grid points we have to solve these equations. So that's the reason we cannot. These equations cannot be solved in this complete form. Not even only if we consider the ocean-atmosphere coupled system, which is only a small subset. Look in this diagram. It's a very small subset of the whole Earth system, which is much more complicated. But even these equations, which are really the base, cannot be solved on a sheet of paper. We can try to find some approximate solutions on a sheet of paper and do some analytical analysis. And the ones of you who will start the Earth System Physics Diploma program will for sure do that. So you can do something with these equations. But essentially, if it comes to really knowing what are the more complete solutions, you have to solve them on a computer. So you have to use very powerful computers to solve these equations. And that's only the basis. That's essentially what I'm doing and what many other people are doing in our section. Solve these equations on the computer. So that's this part. Then, of course, these equations have some forcing terms on the right-hand side. And the most important for the Earth system, and for the climate system in particular, is the external forcing coming from the sun. We will see that later in this course. The sun is the one from this perspective here, from the ocean atmosphere coupled perspective, is the one, the incoming energy from the sun is the one that is driving all our circulations that we observe on the Earth on the large scale. So essentially there's nothing else. There can be small effects from other things, but 99% of the motions we find on the global Earth system for the atmospheric ocean coupled point of view are driven by the energy coming from the sun. So that's the most important forcings. But then it's not trivial, because the sun comes in, we will see that later, goes through the atmosphere, and then there are chemistry processes that may be important. The radiation is absorbed by the gases in the atmosphere, and chemistry becomes important. And those kind of parts are also done in our Earth system, not by myself, but in our Earth system section, people are dealing with atmospheric chemistry. So that would be another part that is attached to this. If you want to do coupled ocean atmosphere, solve the thermohydrodynamic equations, you also at some point, if you want to be complete, have to include the chemistry of the ocean and chemistry of the atmosphere, because that's important to understand the driving part on the right-hand side on these equations. The very first models have kind of ignored these kind of facts and just parameterized in a very simple way how chemistry interactions may take place, and you insert something here that is very simplified. But nowadays, we try to be more complete and really to have equations also for the chemistry part involved in these equations. So that's the chemistry part, but it's not everything. There's more to it. It comes at the end even to include the human component into this system, because if we want to understand how the climate is changing in future, you all know, you have all heard about the IPCC report, where scientists try to understand what is the likely change of the climate in the next 100 or 200 or 1,000 of years. So, and the most important ingredient climate scientists believe there may be the increase of greenhouse gases or the CO2 component of the atmosphere. So we will understand that later. We increase this gas, and this gas is very important for the Earth. We will also understand that during this course. But if it's changed too much from its current value, it can be also quite dangerous. So climate scientists believe that increasing this gas may help to increase the mean temperature of the Earth. That may lead to problems. And of course, the amount with which this gas is increased in the atmosphere and in the ocean depends on what humans are doing, for example. How can we know? We know from the past maybe what humans have been doing, more or less. Not exactly. But in future, we have kind of to try to understand, if we want to predict the climate, even just the mean temperature of the Earth for the next 100 or 200 or 1,000 years, we have to make some kind of prediction how humans will behave, how economies will develop in future, how population development will develop. So if you really want to look at this system in this way, it's a very, very, very complex system. Most of what I am doing personally is still related to the thermohydrodynamics equations, because this is what we understand by now after, let's say, 50 years of good research and modeling. We understand very well. The other components are relatively new, and including this human component is really something that has occurred maybe in the last 10 or 20 years, perhaps maybe more the last 10 years, where these models even try to include the human components. Of course, since you cannot do this exactly, you just propose some possibilities and then look how, for example, the greenhouse gases may change in future and how that may influence the mean temperature and regional temperatures on the Earth. So since it's very difficult to predict this with any certainty, how humans will behave in future, you just imagine some scenarios how we will behave in future. So that's a very, very complex system, and we have to use computer to solve this. Yeah, just look at if you, for example, just look at the Earth from a satellite. It's quite interesting that we see these kind of cloud bands on the Earth that are related to the climate that we really feel at the Earth's surface. So we can see even that there's hydrodynamics going on at the Earth's surface and in the Earth's troposphere, which is from the bottom to 10 kilometers maybe, by just looking at the Earth from outside, from a satellite. We can see how important the hydrodynamics is. Okay, why study the ocean? I don't want to go into this. The ocean, of course, from the traditional point of view, is from an atmospheric point of view, from an atmospheric scientist point of view. I'm concerned about solving these equations for the atmosphere, maybe. Then the ocean is a lower boundary condition. So I have to understand what is happening at the lower boundary anyway in order to solve these equations for the atmosphere. I have to know what is going on at the lower boundary. That's maybe my purpose from an atmospheric scientist point of view. But of course, there's much more to it. Ocean is very important, not only for this purpose, but ocean is important for fishery. We all eat fish, and fish growth depends on micro food availability in the ocean and so on. So there's much more to the ocean than just the pure atmospheric physicist point of view to be some kind of lower boundary condition. Ocean absorbs CO2 concentration. So CO2, this greenhouse gas, is mainly dangerous for global warming, let's say, in the atmosphere. So it's important to know what part of the CO2 output that human put in the atmosphere is absorbed by the ocean, for example. There are many other reasons why the ocean is important. There's no doubt that the ocean is equally important as the atmosphere. So only that we are living a little bit more in the atmosphere than in the ocean. Something important to note. If you go back into the history of climate, you will find that many millions of years ago, actually the atmosphere has been mainly built of CO2, for example. Very little oxygen, mainly almost 100% CO2. And the reason why nowadays we have a fair amount of oxygen that we can breathe to live, and very little amount of CO2, is that plants and animals, bacteria, have been growing. And you all know if a plant is growing, it converts CO2 into oxygen and other gases. And of course, if a plant is decaying, the reverse happens. So what is needed to kind of reduce the amount of CO2 in the atmosphere is that the plant that is dying is not reversing this process, but the material that could reverse the process that has been built, like the wood or if it's like corals, for example, they are not decaying, but they are preserved from decaying. So the CO2 concentration, the oxygen that has been produced by this plant or by the animal remains the same in the atmosphere or in the ocean. And for example, if you look at, this is a coral reef that some time ago has been underneath the ocean, but with the movement of the continents that Karim will probably explain to you a little bit more in his lectures. This has been coming out of the ocean, and this is all material that is actually responsible for the amount of oxygen we have at the moment in the atmosphere. So if this is decaying again, and with time it probably does, but then there are other processes that compensate for that, then all the oxygen that we have would be consumed again, and our atmosphere would be again maybe 90% CO2, and yeah, that would be a real problem. So that's part of the reason why the ocean is so important, because it helps to sediment these organic material and prevent it from reversing the process of photosynthesis. So that's one part why the ocean in the history of climate has influenced climate so much. But let's look at the driving force for the circulations that we are really interested in, for circulations on a more short time scale. Let's say we are interested now on time scales of a few days, 2 weeks, 2 years, to maybe 100 years, but not millions of years. So what's the energy input from the sun? And this is a very important figure. So this is the net surface solar radiation flux. So we are measuring now the solar radiation that is hitting the surface on average. So this is the annual mean. And the numbers that you see here, you probably cannot read very well, are close to 0, something here at polar regions, and they go up to 300 watts per square meter. That's the unit we use for the energy flux at the surface here. So that's the, and this energy flux at the surface is driving our circulations in the atmosphere and eventually also in the ocean. It's this energy input. And actually it's mainly not even the fact that we have this energy input altogether, but it's the change of the energy input from one region to the other. So what do you think? Why do we observe this change of energy input from the tropical regions to the polar regions? Why is there more energy input? Yes?
I think maybe due to the cloud formation when there are clouds, maybe some energy can be reflected. So some areas would receive more energy than the others. Areas that don't have many clouds would receive more energy than
That is one mechanism, the clouds. But that's already kind of a secondary mechanism. But we can see actually, we will discuss this in a minute. We can see the cloud, the importance of clouds. What's the main mechanism?
Can I guess it's because
Of the ocean? It's simply the fact. The last lecture I will be giving here, I will probably talk about the annual cycle. It's simply the fact at which angle, on average, on the annual mean, the solar radiation is hitting the Earth's surface. I mean, you all know, most of you come actually from tropical regions. You all know that the energy input, probably already where you come from, is much stronger than the energy input we get over a year averaged in Trieste, for example. See, in winter in Trieste, cloud cover or not, the angle with which the sun hits the surface is so low that the energy input that the surface really receives is very small. That's the main reason we see a change of the energy input at the surface between equatorial or tropical regions and the extratropical regions. In summer, the situation is a little bit different, as you can see now. Of course, in summer, we will discuss this annual cycle effect later. That's related to the tilt of the Earth axis of rotation with its rotation around the sun. In summer, there's much more energy input also in the extratropical regions. But on average, we can find that there's much more energy input in tropical regions. That's the main cause. And you all know that because you know that it's different living in a tropical or subtropical country than living in Trieste, for example. There's already a big difference between Trieste and the tropical countries. But as the first secondary order effect could be clouds. And we can see this actually. If you look here, you would expect the energy input is purely astronomic formula in principle. So if you calculate what would be the maximum energy input in the annual mean, you would get a very smooth function of latitude on average. So these deviations that we see here, for example, just north of the equator, we have a reduction of the energy, the solar energy input at the surface. That's due to cloud cover. Yeah, that's the reason is that we have the main rain band in the Pacific, in the mean in this region, and as you all know, probably from daily life, if it rains, there are clouds typically, and that means that the solar radiation that actually hits the surface is reduced, is reflected or is absorbed by the clouds, but cannot hit the surface. And we are looking here at the radiation that really hits the surface. Yeah, so the clouds are very important, and that's more or less everything we have to be interested in here. And this is the main driver for the atmospheric and for the ocean circulation. The difference, actually, for the large-scale circulation. So if we think about local circulations that maybe Adrian Tompkins will talk to you about more in his course, convective circulations. Then also just the local effects of solar radiation are important. But for the large-scale circulations that we are mainly interested in, it's the changes between the tropical and the polar regions that are driving our circulations. Yes, please.
Talking about the mean temperature we have, since we can measure the energy that comes from the sun, to compute the temperature, the mean temperature, is it Boltzmann equation that we use?
The Boltzmann?
Yes.
Yes, essentially yes. So you assume that the body, that the Earth acts as a black body, and you can calculate the mean temperature based on this. It's a little bit more complicated to include then the atmosphere into this. So it would be much more easy if you do not have any atmosphere, but just the Earth's surface as a black body, then the calculation is straightforward. And actually, then the Earth's surface temperature in that calculation would be, what we will just discuss this also later, would be quite cold if there's no atmosphere, based on the energy input that we actually get at the surface. So it's important that we have gases, greenhouse gases in the atmosphere. So the effective temperature that is governing the outgoing radiation as the black body is not at the surface, but it's somewhere near 5 kilometers. So we have this. So in the end, what you are saying, and that is right, is that the radiation that comes in a balance has to be, let's just R, has to be something like sigma to the T to the power 4. So that this formula could be used, knowing the radiation that comes in, to calculate the temperature on Earth. If you just use this formula to calculate the surface temperature, you would come to a temperature that is something like minus 30 degrees or something like this. So or minus 18 degrees. To fix this, you have to include that there is some kind of atmosphere involved in here, so you include some emissivity in front of this sigma that accounts for the fact that we have an atmosphere. And if you do that, the effective layer, which on average is radiating this temperature, is at a 5 kilometer height. So this minus 20 degrees you have actually not at the surface, but at 5 kilometer height. And since the temperature is increasing with, if we go down, we will probably also discuss why this is the case, then the Earth's surface temperature is higher than the temperature we could actually calculate from this simple formula. But in principle, yes. In principle, the answer is yes. You can use this energy input on average, if you do the global average, for calculating the mean temperature. Only that you don't get the correct temperature at the surface using this formula, because it's not only the solar radiation that is important then, because we have the long wave radiation that is coming from the greenhouse gases.
Sir, on this picture, can I see the picture again?
Oh, sorry. Yes.
Yeah, if we see that the tropical region, the solar radiation is higher compared to, on the ocean compared to the solid Earth. You see that?
The solar radiation is higher here than it is over the land region.
Yeah, that's okay. What's the reason?
So it's partially actually, that's a very good question. So this is the radiation, let's see, heating at the surface by solar radiation. So, very good further question. Part of the answer to this is that over land we have, so over the ocean essentially, if there are no clouds, 95% of the energy coming in is absorbed. by the ocean surface, because the ocean surface is very dark. Over land, this is not the case. So this is really the heating that we get at the Earth's surface by solar radiation. So what is to take into account over land surfaces is the reflectivity of a land surface. You all know that in the Sahara, for example, even though there are no clouds, a lot of radiation comes in, but we have sand that has a very high reflectivity. So the amount of energy that is actually absorbed is reduced due to this fact. Whereas over the ocean, we don't have this effect. If there are no clouds, we always have a very dark surface at the ocean, and so most of the energy is absorbed. Now, that's a very good question. I forgot to mention this. Even more important, of course, regions with ice. Over Greenland here, for example, an ice sheet, permanent ice sheet, is reflecting almost everything that is coming in as solar radiation. The other reason why we have partially reduced radiational heating at the surface is, of course, again, cloud cover. Then if we go, for example, in these regions where there's a lot of rain on average. But if we look into the Sahara, yeah, the reason why we have reduced energy input is we call it albedo. It's the albedo of the Earth. The albedo of the Earth can change also. So that's a third very important mechanism to regulate the energy input at the surface. And
okay, so these differences in solar radiation, is it the main cause of the different climatic changes?
You could say not of climatic changes. What do you mean, human-induced or generally? Why climate is varying in general, the energy input here. I wouldn't say the main, but it's one of the very important reasons. We think why climate is changing at the moment is actually maybe not mainly related to the energy input from the sun, because this is really the energy input from the sun, and maybe how this is changing by the cloud cover, which is important, and how this is changed by the albedo. But for example, for future climate projections, climate scientists believe that the energy input from the sun that could be also changing is perhaps less important. First of all, we cannot predict it very well, but perhaps less important than the changing of the greenhouse gases that is regulating actually our surface temperature due to some emissivity. We will, however, see this later. So the energy input is very important, and in the past, certainly ice ages that has been observed on Earth has been governed by small changes in the energy input from the sun, actually, or small changes in the tilt of the Earth axis that change a little bit how the energy is distributed for us. So that's very important on very long time scales. But we believe that for the next 100 or maybe up to 1,000 years, maybe changes in the energy input from the sun are perhaps less important than changes of the greenhouse gases, of the long-wave radiation that may be hitting the Earth from the greenhouse gases that we emit into the atmosphere. Yes, but in principle, yes, changes are very important and have to be included if we want to understand climate.
It's somewhat uniform. It is green, yellow, but same, it's not that uniform. Where there some particular areas of red, this high flux.
Here, this high flux. These are really regions where there's absolutely no cloud. There are no clouds here. Therefore, we see these very large. So we call these are the subtropical high pressure regions. If you ever traveled in these regions, maybe Hawaii in the Pacific lies. It's raining very little.
So that one is because of some surface. That one.
Here?
There is one single one up to the left, a little to the yeah, that's one.
This one? No, this is just, this is an annual mean of a 40-year data. It could also be that it's not, this little maximum may not even be stable if we average on a different period. So I wouldn't put too much. I mean, the basic structure is like this, but this little maximum, I'm not 100% sure if that's even really a reliable measure of the climatic mean. Maybe this, if you look at a slightly different period, it would move around here because of randomly changing cloud covers or something like this. So I wouldn't put too much in this. But the basic structure, yes. Here there's more energy input at the surface because definitely there are less clouds in this region. And the same is true for all these regions. Yeah, that is very good that you ask questions.
I saw that it is like 40-year reanalysis of atmospheric data, right?
Yes.
Okay.
Should I explain what this is?
Okay, but how do they plot this? I mean, how do they collect the data?
Yeah.
Just some glimpse.
Yeah, no, another very good question, and I should have told you this before. So this is another point that we will be also probably discussing later in more details. Data collection in the atmosphere. In the atmosphere is already quite good. We are in a good position. In the ocean is much worse, and I guess for the solid Earth part is even worse than that, because it's so difficult to go down into the Earth and do real observations. To get such a picture, 40-year picture, how do we do that? I mean, we need observations at every grid point. Even for the atmosphere, this is not possible. So to draw such a picture, you need observations every 1 by 1 degree, probably, something like this. And this, even in the atmosphere, which is relatively well observed, is not possible, even for the last 40 years. So of course, the way this data set has been created is it's essentially reanalysis. Whenever you read reanalysis, that's hinting to a mix of observed data and a model. So an atmospheric model, an atmospheric general circulation model, so essentially a model that is solving these equations, is kind of used in a very intelligent way to interpolate. So it could be, for example, that we have some measurements here, there at certain points, and the model is used in a most sophisticated and intelligent way to interpolate the data all over the globe. So since the model we can use to space, the spacing of our model can be whatever we decide, we can use the model, and since it's transporting information from one area to the other, we can use the model in a very sophisticated way to do an interpolation of the data. And this is essentially, however, I mean, this is only possible if you have already quite a good observational data set. And essentially, this is very well only possible since we have the satellites that can really measure. I mean, the satellites can almost measure, yes, the global distribution of the radiative flux at the surface. But before that, and the 40-year reanalysis, as you can see, goes back before the satellite area, there were other methods to measure the radiation at the Earth's surface. You can imagine that this is a very, reanalysis is a very important component of people's work in the atmospheric and also in the ocean component, because it's a way to get the best estimate of the observed history of the climate in the atmosphere and in the ocean. Both are called reanalysis. We call it it's not data, But it's reanalysis because the data is combined with the model to get the best estimate of the observed history. And that's a very sophisticated tool to use these models. In fact, they're very sophisticated methods, very interesting methods to do that. I should have mentioned that actually. Okay, so that's our baseline. Then what's happening at the surface? Now we have this energy input at the surface. Radiation, solar radiation comes in. We have kind of written the answer already here. So one thing we have said is partially there are clouds and there's the albedo over land surfaces. So part of the radiation that comes in is reflected, but that's already subtracted here, because here we look really only at the part that is to what is happening at the Earth's surface. So what is happening to the rest? It's obviously absorbed, because that's the assumption we make by using this equation here. The energy that comes to the surface is absorbed at the surface. But when it is absorbed, actually, for this kind of body, locally at the surface, many things can happen. So the energy is absorbed, and of course, it could be, since we have to go into an equilibrium, if energy is absorbed, the body has to lose energy. This is the assumption that we made here. The solar energy that is absorbed is lost by long-wave radiation according to the Stefan-Boltzmann law. That's short-wave radiation. That's long-wave radiation because of the temperatures we have. So there's always this distinction that we can make practically for the kind of temperatures we have on Earth. The radiation that we get from here is a kind of long-wave radiation compared to the incoming solar radiation. But that's not all what can happen. In fact, that's probably not the most efficient way. Most regions at the ocean surface, or also partially at land surfaces, how they lose energy. That's not the most efficient way. What else could you imagine what can happen at the surface? How can the surface lose energy? That it's absorbed. Evaporation is a very important. Yeah, I think we will come to this later. So evaporation is a very important phenomenon. Heat conduction is quite inefficient for ocean surfaces, can be a little bit more efficient for land surfaces. But evaporation is by far more important, an important way to lose heat at the surface, because it's a phase transition, because between the fluid and the gas phase of water vapor, and it's a very efficient way to reduce the temperature at the ocean surface that otherwise may increase every further if we have the radiative energy input. So a surface loses energy because of long-wave radiation that is radiated away, evaporation, heat conduction, and if we look at the local point, there can also be transport of energy. So we can have lateral or vertical transports of energy. We will come back to this later, however. So somehow the ocean surface loses heat from radiation, from heat conduction, but probably mainly due to evaporation into the atmosphere. The evaporative cooling of the surface, however, if it's due to, as I said, evaporation, doesn't warm. So somehow the ocean loses the heat by evaporation, and this heat is somehow transferred into the atmosphere by this, we call this latent heating. But as it says, it's latent heating. So we don't, it's latent, we don't really feel it yet. So what's happening is, where's the heat released? That is lost at the ocean surface, for example, by evaporation. Another change of state, which we find in the clouds. That's the reversal. So everything in the global mean, everything that we lose at the ocean surface from evaporation, which is a lot of energy, is gained in the atmosphere by the condensational heating, which is the reversal. And a proxy of that is rainfall, of course, because rainfall is then what we can measure at the surface. We can measure the amount of water that is actually condensating in the clouds. And that's what's shown in this figure. So that's kind of a proxy, if you want. Below here is a real estimation, but the rainfall is a proxy information of the heating that we have in the atmosphere. And interestingly, so where do we find these regions? It's one thing remains true. There is this change. We have large heating in the tropical regions and less in the polar regions. But if you compare the regions, doesn't fit very nicely. If you compare the regions where we have most of the energy input at the ocean surface, that is then compensated by evaporation, and where we have most of the heat release in the atmosphere by condensational heating in the cloud systems, they're different. You know, here in this region here in the eastern South Pacific, there's almost no rainfall. Oh, I should maybe say the scale here is like this blue color is a lot of rainfall. This is in millimeter per day. And the white color is no rainfall. And then the green is something in between. So in this region here, where we get most of the energy input at the surface, there's no atmospheric heating. Instead, most of the heating is here in the Western Pacific, where still there's a lot of energy input, but much less than in the Eastern Pacific. So they're not the same regions. Why can this be the case? Why is the release of this latent heat not in the same position as the
The Earth is in motion, it rotates.
Exactly, the air is in motion. So the winds, essentially, the winds transport the moisture coming from this region in a complicated way into these regions where we have these heat released. So having a fluid, let's say the atmosphere is something like a fluid system that can move, makes the system much more complicated than just this. Looking at this, okay, we have energy coming in, energy coming out locally, and this must balance. No, it's not like this. There's motion going on that can change where actually then the atmosphere is heated eventually by the solar radiation. But as you can see, it's much more complicated. We have to understand this figure here, we have to take into account motion in the atmosphere. It's important where we have the heat release. Yes?
What about the motion of electron because we know that the formula giving the energy take into account the motion of the electron, which is termed in T-square, I think.
Yeah, that's. I don't know if I understand your question correctly. I mean, essentially, in the end, everything is coupled, so it's very difficult. We have seen this already here. it's very difficult to say something is really an external forcing, because already the cloud cover that that determine here the energy that is hitting the surface is changed by the motion in the atmosphere. Is changed by the equation, by the thermohydrodynamic equation itself. So it's very difficult to distinguish an external forcing, at least here at the surface, from something that is driven by the thermohydrodynamic equations themselves.
Okay. In this model, we didn't take into account the motion of electrons to solve this problem.
The motion of electrons?
Yes.
No. This is... Okay. Motion of electrons, we would parameterize in a very simple way in this equation here. So in this equation, in the thermodynamic equations, what changes the temperature? On the right-hand side, there would be some divergence of the radiative flux or something like this term that can change the temperature locally. So that's what these models are doing. They're called radiative transfer models. So you try to follow rays from different directions of solar radiation from coming from the sun, shortwave radiation. And but that's essentially, that's the whole theory that goes into this, and that could change the local temperature at a given point. Even in the atmosphere. The point is only that the atmosphere absorbs very little solar radiation. Actually, most of the solar radiation goes through the atmosphere and hits the surface. So most of this convergence of radiative flux is actually at the surface. And that is then driving our changes in surface temperature and other equilibrium mechanisms. Is that answering the question? But essentially, that's not, if we want to say, that's not the direct dynamic part of the thermohydrodynamic equation. That would be some kind of a physical parameterization that we use to drive our thermohydrodynamic equation. At least that's my point of view. Maybe if someone is expert on radiative transfer, he would say, oh, this is the most important thing we deal with. But my personal kind of preferred point of view is that I look at the thermohydrodynamic equation, and the radiative flux convergence is a very important driving force in these equations. But things are coupled. So the convergence of radiative flux depends on the thermohydrodynamics, because that's what we see here. Cloud cover changes already the energy input at the surface. It's a coupled problem. So, but we try here a little bit to say, okay, for sure most of the energy input variations are anyway driven by the sun and astronomic formula. But then, where the heat is released in the atmosphere is strongly governed by the motions. By the motions in the atmosphere.
I don't know how much important it is, but we have the Earth's magnetic field lines, right? And then are they really? I don't know how much.
Second order.
Okay. Maybe not, they can trap the thing like I don't know.
Yeah. This is, but not for this picture. Not of first order relevance. Yes, you can have effects of magnetic fields, of course. And maybe for some studies you may have to take this into account. For sure, if you study the ionosphere, you must probably include these effects. Yes. But if you look at just the lower part of the atmosphere, which contains the most mass of the atmosphere, is contained just in the lowest 10 kilometers, more or less, that we call the troposphere. And that means most of the mass is contained, also means most of the energy in the motions is contained in this layer. So if we're concerned about this layer, we probably do not, in the first order, have to take into account these. There can be many effects that are, in the end, if you want to be precise, relevant. But we are discussing here first order mechanisms. Yeah, so this translates into this heating figure, the mean heating at the surface. Not at the surface, this is for the atmosphere. This is the heating, the vertically integrated heating in the atmosphere. Where everything is taken into account. So this also takes into account loss of heat by radiation. And therefore you find regions, since this has to balance on average, everything that is gained has to be lost in the global mean and in the long-term mean. The blue colors here, which are negative, and the red colors here, which are positive, have to balance. So the mean heating of the atmosphere, if we take all processes into account, also the heat loss by the Stefan-Boltzmann law, has to be 0. Otherwise, yeah, we may think the atmosphere may heat up or cool down. But if that's not the case, if we are in a long-term mean state that doesn't change, then the blue colors and the red colors here, so blue colors negative, red colors positive, have to balance each other. And this is very important because the differences here will certainly drive motions. Changes in the heating will drive atmospheric motions. So in the end, we have to transport somehow the heat that is gained here to the regions where heat is lost from the atmospheric point of view. From the ocean, there's a similar point of view. In the ocean, it's the same. The heat has to be transported from the region where it is gained to the regions where it is lost by the atmospheric motions. So that's the important conclusion that we can draw from here. But on average, we have again the picture. Energy is gained, on average, in tropical regions, and energy is lost, on average, in extratropical or polar regions. But as you can see, the picture, if we look locally at it, is much more complicated, even in the tropics. We can have, at the same latitude, regions which have an average loss of energy and regions which have an average gain of energy from an atmospheric point of perspective. That's quite interesting. And what compensates are the motions that we try to understand and try to solve. So essentially, here is a picture of what we do when we solve these kind of thermohydrodynamic equations for the situation, for a typical situation. The solution of these equations, let's say stationary solutions, they're not stationary, but if we just do a long-term mean of these equations, we would find motions that transport the moisture from here to there. And yeah, but the motions are very complex, so they're in the vertical. We will probably not discuss the complexity of all these motions in this course. Particularly not me, because I'm supposed to talk more about the ocean part altogether. But they're very complex motions in the equatorial regions and complex motions in the more polar regions. And things are much more complicated. You will see that the people who join the Earth System Physics Diploma, we will certainly learn that one very important force that has to be taken into account here is the force that is due to the rotation of the Earth. The climate on the Earth would look much different for the ocean and also for the atmosphere if there wasn't the rotation of the Earth. So the fact that the Earth is rotating, and it's a sphere, which makes things even more complicated, gives a very important force in the momentum equations, which is do you know the name? The name of this force? Coriolis? It is Coriolis Force. It's a very important force. And if you look at these arrows here that you probably hardly can see, for sure these arrows look like that these are wind directions because of this very important force. It's one of the most important forces that we have to take into account. Apart from the fact that due to the changes of temperatures, we get pressure differences. The pressure gradient force is the other important force. But those two forces, pressure gradient and Coriolis force, are the most important forces in the atmosphere, probably also in the ocean, to take into account to understand motions that are generated by forces. The Coriolis force is acting everywhere. It's not related to the system we are looking at. So it's the ocean, the atmosphere, and the internal of the Earth, if we are interested in solid Earth things. It's important changes with the medium what we are looking at and how it acts exactly. But the force is completely independent of where we look at. It's there in the ocean, in the atmosphere, and in the solid Earth. It's just due to the fact that the Earth is rotating.
How about at the poles?
Yes, it's a good at the poles. It's a very strong force. Actually, this force is strongest at the poles, because we have the maximum rotation. So the trick is, so if we have our Earth ideally, this is the rotation axis. So the Earth is rotating with this maximum speed for a surface, so an observer, and since the most important motions that we find are actually horizontal motion on the Earth's surface, which is due to the fact of the geometry, essentially. In the horizontal, we have a lot of space. In the vertical, the motions are essentially limited by the height of this tropospheric, of our troposphere, which is 10 kilometers. In the horizontal, we have thousands of kilometers. Therefore, horizontal motions are much stronger. So for horizontal motions, if we draw a kind of a tangent at the pole, this has the maximum rotation speed. If we draw the tangent at the equator around itself, this has no rotation at all. So the Coriolis force, in fact, vanishes not at the pole, but at the equator. The equator is a very special place for the Coriolis force because it changes sign. That's
The coals, sometimes when we open like the water and then it circulates in a unit direction. I don't know.
No, this is a misconception. So the Coriolis force is important for large-scale motions. I think it's better to say for very slow motions, for motion on which the time scale is essentially determined by the rotation of the Earth around its own axis, which is time scale is 24 hours. Then the time scale that we have to take into account to make this Coriolis force acting efficiently maybe then down to, in the end, 6 hours or so. We have to wait 6 hours to see something. So for the rotations that you see in the bathtub, for example, that develops in a few seconds. So the Coriolis force would not be relevant for this. So it's mainly then relevant for large-scale motions, because on a large scale, motions are developing more slowly. And so a few hours may be needed. You can actually calculate. Do you play soccer?
Yeah, I'm not good.
You can calculate the speed with which you have to kick a penalty in order to miss the goal because of the Coriolis force. So you can aim to kick directly, target on goal. And so what's the speed you have to kick the ball? It has to be very small. The speed has to be very low, obviously, to miss the goal because of the Coriolis force is something like.
When we drop a ball, okay, when we drop a ball, since the Earth is rotating, then the ball will not fall directly like.
Yeah, that's a similar problem.
Okay.
That's a similar problem. But so that's a matter of time scales. So whenever we have typically small scale motions, even tornadoes are not. So in fact, the Coriolis force leads to the fact that, motions on a large scale, cyclones, you have seen cyclones in the extratropics, in Trieste, heavy wind blowing for a few days. Those very large scale systems have a preferred rotation direction. Preferred meaning that it's 100% sure that if you have a cyclone, it's moving in a certain direction. But the same is not true for tornadoes, for example. Already tornadoes, which you've heard of, I assume, the very strong wind. But already there's no preferred direction because they're too small scale and therefore the time scale needed to develop them is too small. The same for sure also for the bathtub. I'm sure if you make a statistics, you will find that there's no preferred direction unless you have some asymmetries in your bathtub that causes this, but not due to the Coriolis force. And also on the equator, the water is rotating. There's no problem.
Is this force related to the magnetic field of the Earth?
No. No, it's a pure effect of... It probably is somehow related because the magnetic field is probably related to the rotation of the Earth, but it's you can derive them independent of the magnetic field of the Earth. So what did I wanted to look at? Okay. It's really the understanding of the figures that we see that is important for me. So if you think about an exam or something like this, it's probably we will discuss things we have discussed regarding the figures. But
I'm talking about this. This is just you can learn just about globe, or you can also learn about plutonium. My question: you can use this for studying about petroleum.
oh, geophysics. This very on the edge, I would say. I think if you're interested to gain petroleum out of the Earth, you probably have to wait for Karim's part of this, maybe.
So in space there are many
exploration, this exploration part, you mean? I mean, for sure, in some ways, this is also important for exploration, because if you want to do to build an exploration site, you have to know about the climate, but it's not directly relevant. The thing is, I cannot talk about that because that's the reason we divided our lectures. So it's me talking about the ocean atmosphere part. It's Ricardo talking about the ocean part. It's Adrian who's talking about the thermodynamic, really details of the thermodynamic and atmospheric part. And it's Karim, I think, who's talking about the geophysical part you are interested in. I have to disappoint you, I'm not able to talk about anything there. Also, it's somehow related to, of course, we've talked about organic matter is deposited. So petroleum is one of the most important part of this organic matter that is deposited. But for the perspective of understanding the motions on Earth, on the timescales I'm interested in, this is really only important on the edge. So I will not talk about this at all in this lecture. You be patient then to we have to divide this because it doesn't make sense that I talk about things I don't know about. So in the end, if we now think of a picture, we have seen there are very important variations also in the zonal direction. But a simplified way, physicists like to simplify ways they look at things, would be to say, okay, on average, however, if we do a zonal average at every latitudinal point, we have most of the radiation from the sun coming in at the equatorial regions and less at the polar regions. That's the curve we see here. That's the radiation that comes in. If we observe the radiation emitted by the Earth from outside, by the essentially this mean temperature, which I have eliminated here, regarding the Stefan Boltzmann law, we will find that this curve is much flatter actually. So there's if we look at the difference would give us the net energy input at the equatorial regions and compare that with the polar regions. We find that there is a surplus in the equatorial regions of energy input at the surface and a deficit in polar regions. And since we have to have a long-term equilibrium, that means that the energy must be transported from the equatorial regions to the polar regions in this point of view. So there must be energy transport. And since we have a fluid, it's not just diffusion. Of course, energy transport could be just heat conduction by, if we have a solid body. But we have a fluid. So there are much more efficient ways of transporting heat. We can have circulation cells and things like that. So there are very efficient ways. And then, of course, our aim is to understand what is the contribution, for example, very important question to understand the Earth system. What is the contribution of the ocean and of the atmosphere to this energy transport that is actually needed to go into equilibrium in the equatorial and in the polar regions? Then people have done that with models and with observations using this reanalysis data set, with models using all kind of models that represent the climate. And the answer is that the ocean is responsible for an important part of the heat transport in the equatorial regions, but the atmosphere is doing overall the main job, particularly in the extratropical regions. So outside the tropics, the atmosphere is dominant. Inside the tropics, there may be regions where the ocean heat transport is actually dominant. So again, I'm an atmospheric scientist, so the atmosphere is probably more important than the ocean for this heat transport. But still, the ocean is very important, also from this point of view. So the ocean is important to transport the energy laterally to the polar regions, particularly in the tropical regions, and then the atmosphere is very important. The motions that we see, that we observe every day here in Trieste, are part of these circulations that are driven by instabilities, and their final aim, if you want, their final aim is to compensate the energy between the equatorial regions and the extratropical regions.
Sir, on this picture, I think it is like, okay, but average heat transported by the atmosphere across the ocean?
That's the black line here. And then the atmosphere is just the blue, and the ocean is the red. You add them up, you get the black line.
And then what does it mean, native?
Oh, yeah, that's if you have account for the geometry, then the heat transfer has to be always to go away from the equator. In order to do that properly, take that into account properly, if you write down the equation for heat transfer, you will find that you have to change the sign here to make the heat transported from the equator to the pole. So this change of sign is essentially has no meaning. It's not a negative energy transport. It's just the geometry that leads us to this change of sign in energy transport. It's clear that at the equator, it has to be 0. And then there's a switch of sign. But if you write down the equation for heat transfer, you will find that the proper way to express a heat transport towards the South Pole here is to have negative values here. So it's it's just the geometry that leads to it. Otherwise, the curve would be here, symmetric to the northern hemisphere. So there's nothing special going on here. It's the d by dy that has to change sign at the equator.
Because if it is like the amount of energy, then it has to be something which is positive.
Yes. No, the amount of energy is always positive. Yeah, we go back to this figure, okay. I think we're almost done, huh? Maybe in the next lecture, this is just to prepare you for the next lecture. We will talk about this greenhouse gas problem that is discussed for climate scientists in the last 20 years or so. So we have observed, and again, now observations mean, in this case, if we go back to 1880 here, that's probably observations of land surface temperatures, also interpolated with in some very fancy way to get an estimate of the global average temperature. So again, measures in some way, some estimate of measurements. So the blue line that you see here is the global mean temperature. And if we go in from the 1800 into the 2010, we see that this temperature has been increasing. Unfortunately, it's in Fahrenheit here. But the increase is maybe something like 1 Kelvin, 1.5, something order of that in this period. And of course, it's kind of a suggestion to draw into this curve also the increase of the CO2 concentration. So the coincidence between these two curves, the the fact that both curves show this upward trend has led to climate scientists in the last 20 or 30 years to believe and to make research on the possibility that increases in this gas may have caused the increase of the temperature. How a greenhouse gas actually works, we will discuss in the next lecture. But the pure fact that these curves have such a similar behavior if you disregard short-term fluctuations but just look at the long-term behavior has led to scientists to believe that, oh, maybe it's the human activity that has led to this changes in temperature over the last 100 years. Yes?
How will be a how we can tutorial? Okay, how will be tutorial? And then we will solve the problem, I think, because when we can see.
You will solve this problem?
No, when I see in the tutorial, there will be some problem to solve, or just.
Which tutorial are you talking about?
Homework. I'm talking about homework. There will be no homework.
No, there will be no homework.
So how we are going to.
You study this web page. Read the background material related to this web page. But there's no problem to solve.
We need
here.
some support. Or we will use just the book.
You use the book. There's plenty of things to read in this online book. So whatever you're further interested in, maybe you find even things about petroleum already in there. But
One question. Okay, we have a continuous input of energy from the sun, right? And then, okay, through long time scale, that temperature is, I think, will grow, right? And then if there is no mechanism such that the energy that is continuously is input on the inside surface is going out, then this is always running.
that's a very good question, but this is...
I don't know how the rate of the flow, the outflux.
Yeah. Yeah. I mean, if you look at physical systems in general, I mean, you are all physicists, so physical systems, we have assumed here that the system is in equilibrium, which means that the energy coming in has to be compensated by energy coming out. Of course, there's no... I mean, this is an assumption that for most stable physical systems apply. But it could be that for some time the system is out of equilibrium and there's more energy coming in than going out, then the system would warm up.
So is it a good approximation for how far are we from?
It's a very good approximation, but at the moment the system is a little bit in disequilibrium. So we are gaining, the energy is increasing currently because of the increase of greenhouse gases. So there's some tiny, it's a very, looking at the total amount of energy, which was the average maybe 300 watts per square meter that is hitting the Earth. This disequilibrium is maybe 1 or 2 watts per square meter. So it's less than 1%, but it's there, yeah. And it can last for years, for thousands of years even, until the system is into a new equilibrium, has changed its energy output in order to get into a new equilibrium. But usually stable physical systems are on average in an equilibrium between energy going in and energy going out. But yeah, that's an assumption, which has not to be, there's nothing that says this has to be fulfilled. Before?
The first figure.
first figure we had? This one.
There we say external forces. So how does a volcano affect?
Volcano. You see, volcano, here we come already how studies of the solid earth in climate may interact with each other. No? Volcano studies is probably more something that is related to solid earth, studying the solid earth. But volcanoes are important for the atmosphere because they expel particles that may reduce the sunlight that reaches the Earth's surface. So that's, in fact, that's thought to be the main effect, that if a volcano manages to put particles in the stratosphere, in the stratosphere they can remain, because the circulations are quite, vertical circulations are quite weak. So they remain quite a long time there, maybe for years. Then they can have a very important impact on the radiative balance of the Earth. So this is a very important part where solid Earth and climate interact, if you want. Sorry.
Is this effect local or kind of effect? Focus on nuclear kind of effect?
Depends a little bit, but is also global. So volcanoes you would see in the global, you probably see in the global mean temperatures. So parts of the another very good question. Parts of the variations that you see, of the shorter term variations that you see in this temperature, this global temperature course here, are supposed to be because of volcanoes. So researchers have claimed that with their models, they can show that if they include volcanoes in the modeling of the thermohydrodynamic system, then they can reproduce parts of these oscillations that we see that are perhaps not related to the global warming curve. So volcanoes are very important. Another important feature where solid Earth studies and climate studies interact together, which is more related to paleo, to very long-term climate studies, is of course also that, for example, if we have a mountain, the mountain is influenced by the amount of rainfall that falls on the mountain because it can erode by weathering. On the other hand, the mountain itself, since it's blocking the horizontal flow, is influencing also the rainfall that is created in a monsoon region. So there's a two-way interaction between mountains, if you want, and climate. And this is important on very long time scales, how these two interact, how monsoon climates have evolved because of slow changes in the mountains that have been observed. Yeah. So, but volcanoes are very important also because of their effects on aerosols. Yeah. Okay.
Is the moon another external cause?
The moon is again, yeah, we can see the moon. That means that some perturbation of the radiation is probably given by the moon, but for the Earth climate, it's irrelevant, this energy input. It's important for ocean tides, actually. You all know tides in the Adriatic Sea, or tides are much more important in other regions, and hopefully Ricardo will tell you more about it. But the attraction force by the moon is important to govern the tides on the Earth. But for climate studies, these effects are not, the moon effects are not included. Maybe you can include it, I don't know, but it's unlikely to be relevant. Yeah.
What can happen if there is no ocean?
What if there's no ocean?
Or the atmosphere? What will happen
So many models of the atmosphere do not include the ocean. The only thing you need from an atmospheric point of view essentially is the boundary condition of the sea surface temperature. So in order to answer your question, it doesn't happen. The climate would be probably quite similar if there's no moving ocean, but of course the same is actually true for the ocean. If you have an ocean that is, in order to drive an ocean, you need some kind of winds. So the atmosphere is certainly very important to drive the ocean. The ocean is important for the atmosphere because the temperatures at the surface are important to drive circulations in the atmosphere. So, of course, in the real world, you will never be able to answer these kind of questions. In order to address those kind of questions, what happens in a world without ocean, you can use a model if you are interested in those kind of questions. But the answer is, in theory, you can pose a model where the surface condition is just the temperature, and it will produce atmospheric circulations. So there would be atmospheric circulations even without a moving ocean underneath. So.
Is the Earth system in equilibrium?
Is the Earth system?
The Earth system in equilibrium. Do you think that the Earth is a system in equilibrium?
In equilibrium?
Yes.
Yeah, this is almost the same question. I think, yeah, at the moment, maybe not. Not in an exact equilibrium. I mean, it's in an approximate equilibrium, yes. Otherwise, we would probably have very large fluctuations. And there would be runaway effects. And kind of history probably picks systems that are mainly in equilibrium, because otherwise, if we have the temperature that is increasing exponentially, a system could not survive. So yes, the Earth system is at the moment more or less in equilibrium. But there are very small perturbations from this equilibrium that may cause the temperature to rise or to fall in future. One last one, because... Oh, sorry. Yeah, don't hesitate. Yeah, write this in big letters. Can you read this? I'm not good in ed, right? Yeah, write me an email. Last one. Yeah. What we do here is essentially only look at maps. What we will study if you do the Earth system physics course, we go into the equations and really look what we can understand with the equations. But here, this is more to get an overview of the general picture. It wouldn't make sense now for us to dig into the details of the thermohydrodynamic equations if you're not familiar with the overall picture. Therefore, but in the end, if you study the Earth system, I teach a course on climate dynamics where we look into the very details of these equations. And that's where things are much more pleasant also for me, actually. But I don't think it makes sense to start this. And there would be tutorials where you have problems to solve, lots of problems to solve. That would be next year. Yeah, we have many problems to solve there. But it wouldn't make sense now to do this with you. I don't think. It's more general.